Okay, let's begin. Welcome everybody to this week's GBO Community Zoom. I'm Jim Jackson. Just a few things to report on what's going on at the observatory this week. We had our REU students on site, and we had a summer boot camp with all the NRIO-wide and GBO-wide undergrads, internships, summer interns. Descending on campus, it was great to see lots of activity and lots of science discussed. And thanks to Will Armitrout and Bren Gregory, Jill Molesky for their work in pulling that off. That was a wonderful experience. AAS meeting is coming up next week. I will be there, and a few other folks from Green Bank will be there. We will have a booth, so please come by. I'm told that you will get special swag if you complete a survey, and if there's no better swag than special Green Bank swag. So please, I encourage you to come and visit, and I will be spending a lot of time at the booth as well. So if you want to come by and chat with me, that would be great. Observatory has entered its summer maintenance period, and we're working on some of the annual maintenance items, and that's all proceeding apace. We're going to have a paint crew come in next week and deal with some of the painting issues. So things are in progress, and we're dealing with some overdue maintenance. So that's all wonderful. That's all I have. I'll hand it off to Jay, who will introduce our speaker.
Okay, thanks very much, Jim. Today's speaker is Adam Hincks from the University of Toronto. And let me just remind everyone that to submit questions using the Q&A buttons down in the lower right of your screen. And this presentation will be recorded and put on our website for later viewing. But right now, let me introduce Adam Hincks. He's going to talk about mapping the gas in intercluster filaments with the Sunyaev-Zeldovich effect. Take it away, Adam.
Thank you very much. I'm really happy for the invitation and delighted to be speaking to you today about research I've been doing recently with a number of collaborators to map the gas in intercluster filaments using the Sunyaev-Zeldovich effect. And if some of these terms aren't clear, I hope they'll become clear during the course of the talk. But I wanted to start just by showing a couple of pie charts. So this pie chart, I'm sure everyone here has seen in some form, showing that today the mass energy of the universe is dominated by the dark sectors. So only 5% of the universe today is made up of ordinary matter, of atoms. But there's another pie chart that I've only started appreciating through the course of the research that I'm going to be talking about today, which is about where these baryons actually live in the universe. So here's another pie chart. And less than 10% of these atoms actually live in galaxies in the form of stars or of gas. So 90% of the ordinary matter in the universe actually lives outside of galaxies. So only 0.5% of the universe today is in galaxies. And this led to the so-called missing baryon problem back in the late 90s, when people started taking censuses of the baryons in the nearby universe and found that it was really falling short of the total density of baryonic matter that's predicted by early universe cosmology. And over the past few years, there's been a lot of progress in kind of starting to observe these missing baryons. But the reason that it's so difficult is that a lot of these baryons live in a state that's just difficult to observe. And in particular, about 25% of all the atoms in the universe live, we believe, in cosmic filaments. So this is a simulation of gas in the universe, and you can see this so-called cosmic web. You get clusters of galaxies, in the knots of this web, but then you have these filaments. There'll be dark matter filaments here, but around a quarter of the baryons lie along these filaments in this kind of diffuse, so-called warm hot state. So 10 to 100 times the cosmic mean, 10 to the 5 to 10 to the 7 Kelvin. And this makes them hard to see. So they're hard to see in absorption, particularly for the hotter phase of this gas. They do emit X-rays through Bremsstrahlung, but it's very diffuse, so the X-ray emission is faint. You might look in the radio for synchrotron, but again, the diffuse nature is a problem, and also, cosmic magnetic fields are weak. So on all of these fronts, there has been progress in the last few years, and people have started making detections of these baryons in the filaments. But a fourth technique, and this is the one I'm going to focus in on today, is to use the Sunyaev-Zeldovich effect. So for those of you who might not be immediately familiar with this, the idea is that you have radiation from the microwave background. Some of that, if it goes through an ionized gas, some of those CMB photons will inverse Thomson scatter. So typically we think of the Sunyaev-Zeldovich effect or the SZ effect in clusters of galaxies that are filled with, with a diffuse ionized gas. Because the gas is a lot hotter than the CMB, it tends to impart energy to the photons that are scattered. And so the result is that, this initial black body spectrum that the incoming photons have, the scattered ones have this new spectrum at higher energy. And what that does is it creates this distinctive spectral pattern where at frequencies lower than about 220 gigahertz, you actually have a deficit of temperature in the CMB because these photons have been scattered to higher energy. So in your CMB map, you see these little shadows where you have a temperature decrement, particularly where there are galaxy clusters. The amplitude of this effect is proportional to the pressure of the gas integrated along the line of sight. And the pressure is just the gas temperature times the gas number density. And I mentioned X-rays earlier. You can contrast this to X-ray emission or the Bremsstrahlung, which goes as the density squared. So this is a bit of an advantage potentially with the SZ effect, is that when the gas is diffuse, this squared term doesn't help you. So people have looked for filaments, they've looked for the cosmic web using the SZ, but typically, and it has been done successfully, but by stacking. So the idea is that you find pairs of galaxy clusters that are physically, a few megaparsecs apart, and you find all those pairs in your map and you rotate them and stack them, and you can see like the average signal between your stacked maps. So this, these missing baryons have been spotted through stacking. But the question that kind of the research I and my colleagues have been doing is saying, well, what about in individual cases? Can we see this gas kind of directly in an individual filament? And about 10 years ago, the Planck satellite, the Planck CMB satellite, published a paper where they showed this map. So these are two galaxy clusters, relatively low redshift shown here, Abell 399 and Abell 401. And they saw a so-called bridge of gas between these two clusters, which they advertised as being, a discovery of the missing baryons, or at least some of the missing baryons. This is a well-studied system, both in the optical and the X-ray, and particularly in the X-ray, there's kind of been mounting evidence for an excess of emission, also from X-rays, in this bridge region. And then even more recently, in the radio, just 3 years ago, radio emission was detected, excess radio emission was detected from this bridge region. So this is a really neat laboratory for studying this phase of the gas in our universe. And there are a couple of things that can be improved upon the Planck observation. The first, you might say, drawback to the Planck data is the low resolution. So I've kind of put the approximate beam size here. And you can see that really Planck only had a couple, maybe 3 beams worth of information from this bridge region. And so kind of the question is, can we go to higher resolution and get a better separation of this bridge region from the clusters and really nail this detection? Can you really show that there's a separation, or that the gas here in the middle isn't simply due to the overlap of the gas of these two clusters, and then can you, get a high resolution image of this filament. And then the second question, where you want even higher resolution, is can we start resolving structure within this filament? So this is a simulation, a hydromagnetodynamical simulation, smoothed here to the Planck, or a little bit higher resolution than Planck, 5 arc minutes, and then here it is at 10 arc seconds, and you can see that kind of this wispy kind of subfilamentary structure pops out when you have this high resolution. So to do this, so this is what we've done. We've looked at this bridge using 2 other instruments, the Atacama Cosmology Telescope. it's a 6-meter telescope, so we get down to kind of arc minute resolutions, and that's really what you want in order to kind of see this complete picture, separating the bridge from the clusters. And then for these even smaller structures, we got time on the Mustang 2 telescope, on the Green Bank telescope, or the Mustang 2 receiver on the Green Bank telescope. And this is suitable for kind of those 10 arc second scales, but it's not that great at kind of these intermediate, few arc minute scales. So, you put together Planck, ACT, and Mustang 2, and now we're starting to probe all the scales that are relevant to start exploring what's going on in this filament. So without further ado, here's the map that we made from the Atacama Cosmology Telescope, from ACT. This is a map of that gas pressure of the SZ signal. And you can see this bridge of structure between the 2 clusters. This is in an RA deck coordinate system. The Planck was rotated so that it was horizontally oriented. And this is our resolution here. So you can see here the improvement we get over the Planck beam. And now we have, lots and lots of beam elements looking at this bridge region with high signal to noise. So the question is, so the question we had was, okay, so is there really an excess between these 2 clusters? You might think, well, maybe the clusters are kind of elliptical, and maybe we're seeing gas, from the outskirts of each of them overlapping in the middle, and that's what's giving us our signal. So we fit a few models. First, we fit just 2 clusters. So let's imagine that there are only the clusters here. And we fit an elliptical beta model, for those of you familiar with galaxy clusters. But the point is that it's allowed to be elliptical to each of these clusters. And this was done, by the way, by Federico, who's finishing up his PhD in Rome. So he kind of led the data modeling, and he's going to be on the postdoc market soon. And this shows the residuals for that first model, where we only fit for the 2 clusters. So this is the original map. Here are the residuals. And you can see it does a decent job, but there's still a lot happening in between here. And you'll also notice that the fit to 401 isn't that great. There's kind of this dipole pattern along this direction. But then when we include in our model a component for the bridge region, here's what the residuals look like. This is the best fit location of this bridge component of the model. So if I just flip back and forth, hopefully slowly enough that you can see it changing on Zoom, you can see the improvement in the residuals. And basically, all of the excess goes away when we add this extra fit component. And statistically, this is by far preferred. So when you account for the addition of the extra model parameters, you find a more than 5 sigma preference for including a component in your model that's modeling this filamentary gas, which we interpret as a solid detection of the gas in this filament. Here's what it looks like if I just take a 1D slice along the bridge axis. So here's that 1D picture. This is Abel 399, Abel 401, and the dashed lines are our various fit components. And in particular, here you see the filamentary component of our fit. not making up all of the gas. Roughly 50% of the gas you're seeing here is coming from the filament, but we're measuring this amplitude with a significance of more than 5 sigma. So here's what it looks like now, where it's the same model, but where we haven't subtracted the bridge component of the model. So this shows the residuals. So we've taken away the 2 clusters from the data, just leaving the component affiliated with this bridge region. So you can see it here. And remember, this is the SZ signal is the integrated pressure. But we can use this to extract how much mass there is affiliated with this component. So the pressure, remember, is the temperature times the density. X-ray data can give you the temperature of the gas. So we take the temperature measured from Akumatsu et al. We combine that with the total integrated pressure that we have kind of over this rectangle, and we get a total mass of 5 times 10 to the 13 solar masses. So there's a lot of mass of gas, associated with this filament in our model. And then if you just assume the average baryon to dark matter ratio, you can estimate the total mass in this filament, which is really large. It's similar in size to a cluster, actually. These 2 clusters are huge, but this represents almost 10% of the mass of this 2 cluster system is in this region affiliated with the filament. These are the dimensions in physical units in the transverse and along the axis. Because our measurement integrates along the line of sight, from our data alone, we can't measure the dimension that I'm calling R fill here along the line of sight. But again, you can combine with X-ray data to break the degeneracy. So remember, the X-ray data goes as the density squared. We only go as the density. You can get the temperature again from the X-ray, and you combine the data, and you can fit, or you can solve for the length along the line of sight. This was done a few years ago now, back in 2017, by Akumatsu et al. And they combined their X-ray measurement with the Y signal from the Planck map that I showed earlier. And they combined it, and they found that the thickness along the line of sight was only about 1 megaparsec, which is smaller than these transverse dimensions. So they concluded that it was kind of squashed along the line of sight, and they said it had like a pancake shape. Okay, so here's where it kind of gets interesting. I was reading this paper, and as I was reading it, I discovered that there was a mistake in the algebra, and that there was a factor of 2 missing, and this factor of 2 was actually squared here, so that this was actually 4 times smaller than it should have been. And the lead author, Akumatsu, was very gracious, very helpful in helping us to kind of figure out what was going on and to confirm what we were discovering in the paper. So we got it all sorted out. But the long and the short is that it's actually not pancake shaped. And when we combine our measurement of the SZ signal here, we actually find that the thickness along the line of sight is about 12 megaparsecs, right? Which is a lot bigger than 1 megaparsec. It's actually completely consistent with the value you get from the earlier Planck data. Ours is bigger than the value you get from the Planck data, but it's within the uncertainties. Okay, so we're actually looking through more gas along the line of sight than you have in this transverse direction. And so what we think is going on is that we're actually looking at it at quite an acute angle. So that Abel 399 is kind of more in the background here. And I created this toy model to estimate kind of what this angle of that we're looking at it is. And it's around 17 degrees with a fair amount of uncertainty. And so the idea is that because it's foreshortened, we're looking through a long column here. And that's what's giving us our 12 megaparsecs. And then we can combine that with, we can use all the information we have now to make a measurement of the total density of the gas in this filament, which is just under 1 × 10⁻⁴ per cubic centimeter. And that translates to about 150 times the cosmic mean baryonic density. So it's a little bit more dense than kind of your typical WHIM or warm-hot intercluster medium, but it's still quite diffuse. Okay, so this is all work with ACT, but I mentioned earlier that we got time on Mustang 2 on the Green Bank telescope, and here is our map from Mustang 2. So we observed for 44 hours. We didn't observe Abell 399. So in this map, Abell 399 is down here off of the map, but we spend most of our time in this intercluster region here, getting down to this sensitivity. And then we also spend a bunch of time centered on Abell 401. So far, we haven't done all the analysis that's possible on this map. In this paper that was published earlier this year, we did a preliminary analysis. The first thing that we noticed is we're not seeing yet, at least, those kind of wispy substructures that you might have expected from the simulation that I showed earlier. The other thing we were looking for, is there any evidence of shocks? We know that all the evidence points to these two clusters being in a pre-merger state, so they're moving towards each other. So you might expect that there be some shocks in the gas. We don't see anything obvious, but we do see an excess in fluctuation. So if you look at the fluctuations in here, for instance, they're real and they're about 5 times larger than the noise. One hypothesis that Charles Romero, who's one of the people on this paper, put forth is, we're looking through a large column here, and if there is substructure, maybe it's getting washed out because we're looking through so much. But that's just one idea that we mentioned in our paper. So there's more that we want to do with this particular system. In particular, we want to combine this map from Mustang 2 with our map that we made from Planck and ACT. There's technical issues with that because of the shape of the map and the noise properties. So that's something that we hope to do. We also have a bunch more. We've observed this system more with ACT, so we actually have deeper data in the can from ACT. So we hope to be able to do to look at this in more detail, and ideally figure out what's going on with some of these features that we already see. So for instance, one thing that really jumps out is that this our best fit model is really displaced towards Abell 401. So what's going on here in this link region, or when you get closer to Abell 399, is there some kind of turbulence here that we might already be seeing hints of in the ACT region? There's also, again, from this paper that I mentioned earlier, Akumatsu et al. Saw in the X-ray a drop in the temperature in this region indicated with this green contour. And they suggest that maybe there's a shock front here. The idea is that as the clusters move towards each other, the gas might kind of bow out in the transverse direction and create kind of low-level shocks. Unfortunately, this region falls kind of outside of what we observed with Mustang 2. So it'd be great, and we'd love in the future with Mustang 2 to observe more deeply, say, these link regions between where the filament kind of meets the cluster. And it would be good too to see if in the SZ you can see any evidence of shocks that might be indicated through the temperature drop there. And then finally, just to conclude, this is just one of these pairs of clusters. And in the title of my talk, I use the plural. I mentioned filaments. In ACT, we have a large survey area, almost around 18,000 square degrees. And we've already identified 160 other close pairs of galaxies in our map. And so what we're planning on doing is going and looking at these other pairs of galaxy clusters and seeing what we can do in terms of characterizing these missing baryons that live in this cosmic web. So I'll finish there. I look forward to getting your questions. These were people that were helped lead this paper that I've been this paper that I led, Hincks et al. That I cited here. And then, there's a long author list. So a lot of people went in both on the ACT side and on the Mustang 2 side to make these data possible and to contribute to this analysis. So thanks for your attention. It's been a pleasure speaking to you.
Thanks very much, Charles, for a most interesting presentation. Let me remind everyone, if you have questions, to submit them through the Q&A button on the lower right. And we have a couple questions already. What is the difference in redshift between the clusters?
That's a really good question. Let me go to my extra slides. Right. So the redshift difference is a velocity, translates to a velocity difference of this around 500 kilometers per second. If you look at the masses of these two galaxy clusters, they have to be gravitationally bound. So we interpret this as a peculiar velocity difference of their velocity towards each other. And one cute thing we did in this paper was to use this to look at the dynamics of this system, and you can actually get a rough estimate of the age of the universe. So if you treat this as a two-body system, at the Big Bang, everything's next to each other, basically. And so the dynamics probably were the following, that they start by expanding with the Hubble flow, then their own gravity takes over, they turn around, and now they're approaching each other. And if you do this two-body problem, that you can calculate an age of the universe, it's large error bars, but consistent with what we know. So that's a long-winded answer to the question about the redshift distance.
Another question: do you have any quantified parameter to measure the turbulence?
No, at this point, all we did was just measure the amplitude of the fluctuations. So I mean, that is quantitative. So we have a noise level, and we find that the actual signal that you're seeing here is about 5 times larger than that noise. But that's the only quantitative number that we have.
Another question: do you have an idea if it would be possible to detect these filaments in the optical, for example, with deep H alpha images?
That I don't know. That's kind of out of my own wheelhouse. One of those earlier Planck papers did use optical data to look at the stellar populations in the filament. And one of the things, if I'm remembering correctly, one of the things they concluded is that the stars are old in the filaments. The filament is old. But in terms of that specific question, I don't know the answer.
Okay, another question. Can you make any conclusions from the Mustang 2 maps, or do you need deeper data?
We would love deeper data to answer some of the questions that I was posing here. I think though in the near term we can also do this, combine all the 3 of these data sets and just get like a complete picture. And as I mentioned earlier, we have a lot deeper data now with ACT, which might help to answer some of these questions that I asked here. But it would be great. It'd be great to get more time on Mustang for this, and also for these other candidates too. So some of these, so this is at low redshift. Some of the cluster pairs that we have in our ACT data are at higher redshift, where they're actually closer together in angular scale, where with ACT we would have a hard time making a map like this. If you go to Mustang, so some of these would be, say, 2-3 arc minutes apart. If you go to Mustang, then you can kind of do with Mustang what we've done with ACT, make a map like this, but now, on a smaller angular scale. And with those small angular scales, we just can't do it with ACT because we're limited by the resolution.
There's another question. Did the Planck observation see the lower energy deficit along the bridge region?
By that, like the SZ, the SZ deficit?
I presume so, yes.
Yeah. I think so. Here's the Planck map. And they did an analysis, and they also found an excess in the middle. Kind of the lingering question was, given the low resolution, how if you only have one beam on that, how solid is that kind of detection of the excess? I mean, I think statistically they made a good measurement. But one thing they mentioned in kind of the conclusion, and also this follow-up by Beaujon et al., is that you really need higher resolution to kind of characterize the gas well, which is what I think we've done with ACT. But Planck did a really nice study, and I think what we've found is quite consistent with what they were able to do at the lower resolution.
The question as to whether the structure of the gas, as you can determine it, might have a fractal nature.
Oh, that I don't know. And I think that's a question where, so one thing I think that we're looking to in kind of our little subgroup is, can we make better use of simulations to understand what we might expect to see with higher resolution. In terms of a fractal structure, I don't know if it would be technically fractal or not, though.
Oh, the questions keep coming in, but let's see. I've noticed in the Mustang map of Abell 401, there doesn't seem to be a strong SZ detection of the main cluster. Is the main cluster subtracted in the Mustang map?
That's a really good question. So Mustang, so this map is at about a 13 arc-second resolution. But so Mustang does this kind of daisy scanning pattern, and it's not really sensitive to scales above about a couple 2 or 3 arc minutes. So on kind of more than 2 or 3 arc minutes, we don't have any power in our map. So that's the reason you don't see the Abell 401 jumping out, because Abell 401 is a big smooth structure, and Mustang 2 isn't sensitive to those large scales. So really that hammers home why you want, for a system like this, you really want all 3 instruments to get a complete picture. Mustang gives you these small resolutions, and then ACT fills in between about 2 arc minutes and 10 arc minutes, which is really crucial, as I've shown. And then Planck gives you the larger scales, where actually ACT isn't very good on those larger scales because the atmosphere creates a lot of noise. So it's really a lesson in complementarity between instruments.
Are the galaxy pairs you're studying similar in mass?
Yeah. Their Abell 401 is bigger, but maybe I can't remember the exact number, but they're similar in size, around just over 10 to the 15 solar masses in the M200, if I'm remembering correctly.
Well, we have time for one more question, and here's the question: are there any of your other cluster pairs separated by enough so that their redshift differences would be represented by the Hubble flow, and you'd get a long throw along a longer filament?
So I guess the question, if I'm understanding correctly, is, are there pairs where you might have a much longer filament? Is that?
I think where they might not have even had time to start turning around.
Yeah, I don't know off the top of my head whether that's the case. Unfortunately, I don't know that.
Well, thank you very much for a most interesting presentation. And we'd like to remind everyone again that this has been recorded and will be available to be viewed through the Green Bank Observatory website. Please join us in 2 weeks when we'll have a presentation by Dongji Li of Caltech on the magnetoactive environment near fast radio bursts and pulsars. We hope to see you then. Thank you.